So let's start, and today what we will review, I imagine that a lot of this stuff you have already seen, but Ranjadharimi advised me to go through it. In case I go too quickly, just you let me know. While I told, say, please slow down, okay? Otherwise, so don't be afraid of doing this. Now, so what we will do is we will go to what is called the Galilei relativity principle. And the Galilei relativity principle, it applies to non-relativistic mechanics. Non-relativistic. That is the mechanics you have studied up to now. That means mechanics in which particles move at a speed much less than c. And the Galilei relativity principle says that it is impossible. This is, if you want, a phenomenological description. It is impossible to detect differences in the law of motion it is impossible to take differences in the laws of motion in system moving with constant speed, one with respect to the other. Okay, so that means you have a frame, for example, the laboratory frame, this room in which you are addressed, and you have another frame moving with constant velocity with respect to this one. Then, if you have a particle doing some motion, and you have the law of motion, it is impossible to detect any difference in the law of motion looking at this particle that moves from this frame or this other frame. These things is a sort of phenomenological formulation, but there is another one that is more mathematical precise, and I prefer this. The form of the law of motion do not change going from one frame to another, moving with constant velocity with respect to the first. Let's see if the English. The form of the law of motion don't change going from one frame to another, moving constantly with respect to the first. This is more mathematical because it means, look, the law of motion, Newton's law of motion is m dx squared d2 squared, and it says that if you go in a new frame, you will have new quantity, but the form of the law of motion is the same. Okay, so it means these two are equivalent. This is more physical or phenomenological. This is more mathematical. It says, look, the law of motion in non-relativistic mechanics don't change if you go from one frame to another that is moving with constant velocity with respect to the other. Okay, so this is the Galilei relativity principle, and it is experimentally verified, and so it was promoted to be a sort of postulate, but it is experimentally verified, and is easy to check. By the way, systems that move with constant velocity, one with respect to the other, are called the inertial system. Okay, now let's see how we can verify it. So let's take away these more phenomenological things and let's stick to the more mathematical one. So it's called relativity because somehow these two systems are totally equivalent. There is no manner that you can distinguish them because the form of the law of motion is the same. The form, it means, here there is a second derivative, here there is a second derivative, here there is a coefficient that does not change, that is the mass, and here there is an object, is the force. That, of course, the force, in the first case, you measure the force in this frame, in the second, you measure the force in this frame, but actually, the two forces are the same. You have extra forces only when there is an acceleration involved, and here there is no acceleration involved, okay? So let's take, for example, the free motion. The free motion is this, if there is no force. Now let's make, let's go to the new coordinate. So this one is x and t. This one is x prime and t prime. This is the new frame. So let's see how this change. So this is the free particle. Let's see how this change when we go into the new frame. The new coordinate x prime, you see there, is x minus v of t. If you take a point here and you want to measure its coordinate, this one, you see that is the same as x coordinate, but you have to subtract the piece that was done by the translation, that is vt. So here there is the hypothesis that at t equals 0, the two frames are one over the other, they are superimposed, and then at time t equals 0, they start moving. Then if you measure the distance here, so this is x prime, and this is x, then the relation is the following, that x prime is x minus vt. Let's use this and replace that here and see which law we get. So we can invert x is equal to x prime plus vt. Now let's insert this here. Let's insert that here and we get m. Then we have dx prime, the second derivative of dx prime dt prime. Then we have the second derivative of this, but this is only first power, so it gives 0. So we are left with 0. So this is the law of motion in the new frame, and you see that are the same. Okay? So that confirms the relativity principle of Galilei that says two systems in relative motion, one with respect to the other, at constant speed, have the same law of motion. They don't change. But what does not change, I mean, you see x prime change, but it does not change the form. Here is second derivative, here is second derivative. It's not that we develop a new form in which there is, so basically, if the law of motion is something like g, x dot, x double dot, mass equals 0, that they keep the same form. It means this g is the same, the new quantity change. And also the mass could change. So the g, the form of the function. So this, imagine, is the law of motion that has the position, the velocity, the acceleration, and the mass, and this sum combination equals 0. The form, this g, that is the form of the function, is the same, but the variable are the new one. So you see, yeah, The variable are the new one, but the form is the same. It's the multiplication of the mass times this second derivative. If in doing that we had developed something like plus k dx prime dt, then we would be in trouble, because then the form of the law of motion is not the same. So that is the Galilei relativity principle. And you know, it was not so clear to Galilei and Galileo and so on, but somehow it became clear when things started going wrong, in the sense that at the end of the 18 well, so these basically, so let's say the form of the law of motion the form do not change going from one frame to another with constant, moving with constant velocity. Now, here, I said the transformation is the following. X prime is equal x minus vt. And if you have a particle, for example, let's see, this is how the position of the particle transform. Let's see how the velocity transform. Suppose this is the velocity of this particle, will be equal to the velocity of the other particle minus v. This is the composition law of the velocity. It's clear that if a particle moves with speed w1 prime in this frame, it will move in the other with speed w minus v, because the frame is moving, okay? One with respect to the other. This is the composition of velocity. Well, what happened is a big surprise happened with the Maxwell equation. With the Maxwell equation, they realized that they are not invariant under that transformation, so they seem to violate the Maxwell relativity principle. And not only the velocity did not compose in this manner. For example, they discover via an experiment due to Michelson and Morley that C prime, the velocity in the new frame, is the same as c, and c is the usual velocity of light, 3 roughly 10 to the 10 centimeter per second. So there is an experiment where they prove basically that the velocity of light does not change from frame to frame, and second, the Maxwell equation are not invariant under Galilei transformation. When I say Galilei transformation, it means this, especially this. What happened is that Lorentz, before Einstein, he was a physicist, but as a mathematician, found which are the transformation under which the Maxwell equations are invariant, and now we will derive them as he did. Basically, we will go in detail into a moment. We will see that there is a slight modification of the Galilei transformation. That modification is due to Lorentz, and it goes back into the Galilei transformation when the velocity is low. But basically there was these extra things. That means the velocity of light somehow different than the other velocity don't get composed in this manner, moving from one frame to the other, but they remain the same. So what Lorentz did, well, you can take the Maxwell equation. From the Maxwell equation, you go to the wave equation for the electric or the magnetic field, and then you realize this wave equation is invariant a different set of transformation. But let's first, so this is the Galilei relativity principle. Let's see which will be the new relativity principle. Let's call Lorentz Einstein relativity principle. Well, the first one, it is made of two parts. The first one is the same as the Galilei one, in the sense that you cannot, the form of the equation of motion remain the same when you move from one frame to another, moving with constant velocity to the other. But the second postulate is C does not change going from one frame to the other. Now, what we have to do now is to derive these two composition law, and we will do. But this is the new relativity principle. And if you use this new relativity principle due to Lorentz and Einstein, then you will see that you recover this when the velocity of your point particle is much less than the velocity of light. Okay, so the first one is the same, that the form of the law of motion don't change in going from one frame to another one, moving with constant velocity, constant in time, okay? And the second postulate that they have to do is chi does not change in going from one frame to the other. The transformation will be different, and I will write down then we will derive x. The new transformation is the following: x prime is equal x minus vt divided by a factor that is 1 over v squared c squared. And the same, we will derive the composition law of the velocity. Maybe I can write, but then we will derive it. Okay. Now, let's see first now how the two are related. I mean, they cannot be in contradiction. So from this one, we go into this when v is much smaller than c. So if you have two frames, one moving with respect to the other, but v, the velocity of one, is much less than c, then we will see that the Lorentz-Einstein relativity principle goes into this one, and the transformation are those one. Let's first notice one thing. So all this was triggered by the fact that the Maxwell equations are not invariant under the those transformation, the non-relativistic one. And second, by the experiment of Michelson and Morley that I will not, it was an interferometer experiment, but I will not waste the time on that. If you can read in those books, especially the one that the PDF is available in the library, the one of Schwartz, you can read the detailed analysis of the Michelson-Morley experiment. One thing that immediately, one immediate consequence of this is this fact, the fact that the velocity of light is the same irrespective if you move with respect to the source or if you are adrift with respect to the source of light, is that simultaneity is not anymore a concept that is invariant with respect to the change of frame. That means two events that are simultaneous in this frame, the laboratory frame, are not simultaneous in a frame that moves with constant velocity. Let me show you how it goes. Then we will go in detail in deriving this, okay? So, first one. Okay, so let's see a first consequence, and this is a consequence of this. The consequence is the following: events which are simultaneous in one frame are not anymore simultaneous in another frame, in another inertial frame. We use the word inertial in the sense, with the meaning that it is, one is moving with respect to the other with constant, and in another constant velocity, inertial frame. Okay, so this is a sort of theorem derived from this postulate. Let's see how it goes. Okay, let's take two events. An event is something that is characterized by a position in space-time and time, okay? So, and let's put somebody here. And let's suppose two events are simultaneous. Then let's suppose that when they happen, this person sends a beam of light to this, and these events send another beam of light to this, okay? Now, this man sits exactly in between the two, so the two are simultaneous. That means when he will reach the signal from them, okay, so this one, there is an event here, and when it happens, it sends a beam of light to this person, and the beam of light will take an interval of time that is this length, L over 2. This is L over 2. So L over 2 divided by the velocity of time. After that interval of time, we reach the man and we register that this event has taken place. The other delta t, let's call this 1 and this 2. Delta t1, delta t2, the same. He sends a beam of light when the event takes place. And these delta t prime and delta t2 prime, we can say that the two events are simultaneous when these two intervals of time are the same. Okay? So an event happens, he sends a beam of light as soon as it happens. The other, as soon as it happens, his event sends a beam of light. If the two events are simultaneous, he reaches them. They reach the man at the same time. Okay. Now let's go in a frame that move with constant speed. Okay. So we have this again. We have the man, but now we are in a frame that moves with constant, or otherwise we take this and move with constant velocity. Then in an interval of time delta t, so this one sends a beam of light, this one sends a beam of light, but as this frame is moving with velocity v, this man is moving toward this object, object 2, okay, so here is moving away from this one, he sits at L over 2, so when will he receive? He will receive after a time that is L over 2 divided by c, but then he has moved, so there is the velocity with which he has moved by some small interval that is delta t1. Okay, so you understand what I mean? He's moving, so he will reach, light will reach him, not with the same interval of time as before, but light has to travel a little bit further because this object has moved, this man has moved here. Okay? And and as he has moved here, there is a distance delta x, and then the interval of time delta t1 will be equal to L over 2 divided by c plus delta x, while the second interval of time is L over 2 times c minus delta x, because this beam of light, does not have to travel L over 2, but it has to travel a distance that is less, because this man has moved, because we are in a moving frame. Okay? So now delta t1 and delta t2 are not equal, so for him the two events are not simultaneous. This is a crucial, if you have not an... Delta x is this.
Yeah, and this is time, right? Delta t1
is the distance covered to reach L2, okay, and then there is an extra piece because he has moved the man, so delta x.
times something, right?
Okay, and below the delta 2 is the same distance, but this man has moved in this direction, so I have to subtract this delta x. Okay, so this thing, delta t1, is different from delta t2. That means the two events are not simultaneous anymore for him. Okay, please. Any question?
You are adding the distance and
Subtracting.
is delta x.
Okay, I see.
Delta x is the distance that this man has moved because we are in a moving frame. Okay?
I mean the dimension. Okay, in the right we have
Oh, yes, you have, of course, to divide by c. You have to divide by c. Okay? Actually, no, you have to divide by v. You have to divide by v. Okay, so the first thing is events which are simultaneous in one frame are not simultaneous in another inertial one moving with constant speed with respect to the other. This is the most important consequences. Now let's go and see all the, remember the Galilei transformation law was x prime is equal x minus vt, and I said the Maxwell equation are not invariant. Under this. So there must be a different transformation law, and the different transformation law now we will derive, or we will do. Let's do in the following manner. Well, you know, when you have the Maxwell equation, mostly you have the Maxwell equation, but you can combine them having in an equation that is the wave equation of the front wave of light expanding. So basically you have a source, and you have, if you take a spherical wave, you have a spherical wave moving out, and this is the essence of the Maxwell equation. Now, which is, can we describe this motion? Yes. This motion of this front wave, and the equation of motion of this is the following: x squared plus y squared plus z squared is equal to c squared t squared. Okay, so if I want to describe all x, y, and z of a front of a spherical wave, and this spherical wave is light, is changing with time, this is the equation. Now let's remember that the Einstein, that the Galilei relativity, the Galilei transformation, the Galileo transformation was x prime is equal x minus vt if we move along x. So y remain the same, z remain the same, and t remain the same. Often this is said that time is absolute, it does not change. it is the same in all frame. That means the clock moves in the same manner in all frame. Now let's see if this, that is the equation of motion of derived from Maxwell equation, is invariant under this transformation. So now we will check if this equation of motion for the wave is invariant under this. Okay, so let's put in the new things, and what you will get is, what we want. We want that according to the first, that the law of motion don't change if we move into a new things. We want that this spherical wave goes into a spherical wave. Why? Because if we change a shape, that means, for example, this is a spherical wave, it becomes an elliptic, then there would be a manner to detect motion. So in order not to detect the motion according to the first principle, that the law of motion have the same form in going from one frame to another, it means this is the law of motion of the front wave, the spherical wave. We want that it remain the same in the new coordinate. Let's see if that is the case using this transformation. Now, so now we insert this transformation, and what we get x squared minus 2x vt plus v squared t squared plus y squared z squared equals c squared t squared. Now there are three pieces that remain the same, but then there is these two extra pieces. So we want, you understand the point, huh? We want that, as this is the law of motion of a spherical front light, it remains spherical, so that there is no manner to detect motion with one with respect to the other. Okay, and we have made use this law, and even made the further hypothesis that C is the same. There is these two extra pieces if we use this law of motion. So we have to find a manner to take them away. And you see, these two extra pieces involve time. So we could try to do the following transformation. X prime minus equal x minus vt, y prime equal y, z prime equal z. But then we could say, well, listen, because there is t, and we have to get rid of this t in these, because these pieces are the same. But there is these extra pieces, so they are not invariant. Let's suppose that t prime is equal t plus f of x, where f is some factor that we could determine. Okay? Then, if we use this new transformation law, this equation would become the following: x squared minus 2x vt. So before I transformed according to this law, and now let's run, and I get this. Now let's instead do these same things, but using this law. Okay, so, and we get this plus v squared t squared plus y squared plus z squared equals c squared t squared plus 2c squared ftx plus c squared f squared x squared. Now, this f has to be determined in order to get an equation that is like this. If we choose f to be minus v over c squared, this equation becomes x squared 1 minus v squared over c squared plus y squared plus z squared plus equals c squared t squared 1 minus v squared c squared. Okay, so we have basically just to get rid of these two factors. Or we get rid of these two factors. Well, besides this, putting an f there, let's rescale everything by a particular factor. So let's forget about this. Now we know that the new law has this form, but still there is this extra piece. So in order to get rid of this extra piece, what we can do is divide by this extra piece, 1 minus v squared c squared, divide 1 minus v squared c squared. Then if you do this transformation, you get rid of this, and you return to this same form. So the transformation, the correct transformation, are x prime equal x minus vt 1 minus v squared c squared, y prime equal y, z prime equal z, and t prime is equal t minus v c squared x over 1 minus v squared c squared. I repeat what I did. I took the spherical front wave. In new coordinates, I want that it has the same form because of the relativity principle. If it were not a sphere but an ellipse, I would be able to detect the motion. Instead, I don't want to detect the motion in going from x to x prime, that are two frames, one moving with respect to the other with constant speed. That this is not what happens is if I insert the Galilei transformation, I get these strange things. So I modified. And I modified first just without this denominator, but modifying t. This is a very important thing. It means t is not an absolute variable anymore. T gets changed. And I put a generic f without the denominator. I get that the new law becomes this. And if you choose f to be this quantity, you get down to this. Now you have only to get rid of this and this. And you can do that by putting a denominator here and here. So the final law, transformation law, is this. These are called Lorentz transformation. And this is how Lorentz basically found them. He looked at which are the transformation under which either the Maxwell equation or a spherical beam of light would remain the same in form, obeying the first principle. Okay? Is this clear? Any question? Now, of course, Lorentz, well, he went further than these, but now these are the transformation. And look, immediately you see that if V is much less than C, then you do an expansion here, and you get that x is equal to x minus Vt plus correction order V squared C squared. Okay? And the same t prime is equal to t plus correction Vc squared. You see, so basically the Galilei transformation that we had before, that were just these, are obtained by these when the velocity of the one frame with respect to the other is much smaller than c. So basically the Galilei transformation were not wrong. They were right in the correct regime that is called non-relativistic regime. That means when the velocity is much less of the velocity of light. So Lorentz was happy about this. Now, you see, in the Maxwell equation, the only velocity involved is the velocity of light. And somehow there we are always in a relativistic regime because the only quantity of interest is the things. Now let's see if we recover. You remember that these, now we have to see if these transformations are consistent with this. With the first one, they seem to be consistent. They send spherical front line into spherical front line. Let's see if they are, remember that one consequence was simultaneity. Let's see how we get that simultaneity is not preserving going from one frame to the other. Let's take the second equation. T prime is equal to t minus v c squared x 1 over v squared c squared Okay, let's take the differential of this. We get delta t prime is equal delta t minus vc square delta x 1 minus v square c square. Now, let's remember when we did the simultaneity things. Okay, in the frame addressed, delta t is equal 0. The two events were simultaneous. So the difference in time is simultaneous. But delta x is different from 0. Then what you get, that delta t prime is equal to minus vc square delta x 1 minus v square c square. And so from here, you see that even if they were simultaneous, the difference in time is delta t. Here, they are not. Delta t prime is different from 0, non-simultaneous. Look, they are actually simultaneous. That means delta t prime goes to 0 if v is much smaller than c. If v is much smaller than c, this is basically 0 and this is basically 1, and then you would get that delta t prime is equal 0. So in the Galilean frame, in the Galilean non-relativistic framework, the delta t simultaneous would imply delta t equals 0. If you are in this regime. But if you are not in this regime of v being very small, they are not simultaneous. The interval of time between the two, so the two events are simultaneous, their difference in time is delta t is equal 0. When they, so basically they get delta t equals 0, it means they reach the man, the two signal at the same time, because the two events were simultaneous. Delta t prime different from 0, it means one reached the person after the other, so they are not simultaneous. Delta t prime is the difference in time to reach the man, but it's also the difference in time that there is between the two events. Okay, so somehow this postulate that as a consequence has the relativity of simultaneity is comes from this equation. Okay, but now the point is this: from the transformation law of x, we should be able to see how the velocity compose. You remember the composition of velocity in the Galilean frame? Okay, note that we derive, it's not that we derived, but we have seen that Lorentz derived this transformation. You can say, oh, maybe there are other transformations that live invariant. The spherical front wave is sent into a spherical front wave. In the book, in the first of the three books that I suggested, they do really with the Maxwell equation, but it's a little bit more complicated. I took this derivation instead, you will find in the note, but from the second book. Basically because at the end what is important is the light front wave. Spherical wave have to go into spherical wave, otherwise you would be able to detect the relative motion. Now, the next things we want to do is composition of velocity. That means, let's suppose we have an object that moves with velocity w. Then if we are in a relative frame moving with velocity v, this is the velocity of an object, a particle. This is the velocity of the frame. Then the new velocity in the new frame is this. Okay? This is the composition of velocity, and this is the Galilean wave. Now let's see the composition of velocity here. Why this is important? Because we have to, we have derived these things. but we want to see if what we derive is consistent with this, that c does not change in going from one frame to the other. Here, in the Galilean things, if the particle that moves is the photon and is moving at velocity c, it would change. The new velocity would be c minus v. Okay, but instead I have this postulate. So that says that c does not change. So I have to make sure that these transformations are consistent with this postulate. Okay, well, how we do? Let's take the differential of this and this. So we take the differential, we get dx prime is equal dx minus v dt 1 minus v square c square, and dt prime is equal dt minus v c square dx 1 minus v square c square. I've taken the differentials of space and time of that equation. And now let's take the ratio of the two, dx prime over dt prime. So this over this. I do the same here. I get dx minus v dt, dt minus v c square dx. And from here you get dx dt minus v 1 minus v c square dx dt. Now this is the velocity of my object that I call w minus v, and here I have 1 minus v c square w. Remember, w I call the velocity of my particle, and v the velocity, the relative velocity of one frame with respect to the other. So this is the composition law. This one would be v prime, w prime. So w prime is equal to w minus v 1 minus v c square w. This is the Einstein or Lorentz composition of velocity. Let's write it below here. W prime is equal w minus v 1 minus v c square w. You see it's different. But again, this one, so this is called Lorentz composition of velocity. W and W prime is the velocity of the particle in the two frame. V is the velocity of one frame with respect to the other. Now, can we go from one to the other? Yes. If V is much less than C, this is basically 0, and we are left with 1, and you go into this. So again, with V much less than C, the Lorentz transformation goes into the normal Galilean transformation. But here now we see the important things. Let's suppose that the particle we have is a photon. It means it's going at the speed of light. So W prime is equal W minus V, 1 minus V c squared W. Now let's choose W to be a photon, so to move with C in the laboratory frame.
Sir,
Please.
is it V or W? I mean, is it, I think W has to be much more than C to get the Galilean.
Let me see. This is W.
Yeah, so we have to say W has to be much more.
Not only V, but also W has to be less than C. So the particle has to move in the, is right. The W, the velocity in the laboratory frame has to be less than C, and also V, the velocity with respect one to the other. Now let's suppose that that object, that particle that we are measuring its velocity is a photon, so is C. So let's put here C, we get C minus V, 1 minus V C square C, and this is C. Do the calculation is C. So you see, the new velocity, you understand why C, this is, you get C, then you multiply, you get C, it cancels the denominator, it goes up and remains C. So this object is C. That means the new velocity of that photon in the new frame is again C. So basically it does not change. And then it is consistent with this. So this strange composition law is such that the velocity is invariant, and so it obeys the second postulate of relativity. There is, please.
Is the transformation unique? I mean, to preserve
If there is only that transformation that preserve, that's a good question, I don't know. Well, you know, you require various properties to the Lorentz transformation. First, that they are linear. You see, they are linear transformation. And you want that because you don't want to send the spherical beam into a non-spherical one with you know, if it were not linear, you would get, instead of x squared plus y squared plus z squared equals ct squared, you would get x cubed, x fourth if it were not linear. So the request, I think, somewhere it must have been proven that the request of linearity and that it goes in the limit of small velocity into the Galilean one uniquely fix the things. And then if uniquely fix that, it uniquely fix also the composition of velocity. But I cannot tell you where to look for the proof. There has been a lot of axiomatic done on, that means done on these, and there is a book, I think, Bridgman, an old book where everything was proved in a very axiomatic way. I forgot the title. I think the author is Bridgman, but I'm not sure. And
maybe could you send us?
yes, I have to look. It is a book I looked 20 years, more than 20 years ago, so I have to find out. I'm an old man, so. Okay, now, this is the composition of velocity along x, okay? You have seen, we have looked only along x, because the frame moves along x. Now, one question you can ask, and we will work out the mathematics now, if this frame moves one with respect to the other along x, do the velocity, if the particle, if we have a particle that has a velocity that is not only along x, but also along y, does it change, does it transform or remain the same? Here, for example, it would remain the same. If you do the derivative, you would get that wy is equal to prime is equal to wy. But let's see what happens instead in the relativistic case. So this is called the composition of velocity. Now, slow me down, okay, because I know that I go fast. So, I mean, some people might have already seen this material and they understand immediately, but some other of you might not have seen, so don't be ashamed to say, slow down, I have understood nothing. Okay, and I will go through it again because we have enough time. I prefer, you know, to finish the 20 lectures in time than not finish 2 lectures before or 3 and I've lost many of you. Okay, so last year what happened is I lost several people and then they asked the question over the last 2 or 3 lectures, but I would prefer instead that you stop me, so don't be afraid or ashamed with respect to the others. I have not understood, you went too quickly, and so. Okay, so now the new things that we will do, you will see the pages for each things are label 1, 2, 3, even with my terrible handwriting, and it's through italics, this handwriting, okay? You know, when on the computer you choose the character italics, that beautiful things, that is not italics. Italics is this, because I'm from Italy, so, and anyhow, you will see that sometimes I insert pages. For example, on page 7 of this note, I have inserted 2 other pages I call 7a and 7b. Okay, so in case you... Okay, so now we want to see, this is the Lorentz transformation. And you know, the point is that Lorentz made this transformation, but he did not believe in them. because there were several crazy features like loss of simultaneity and the fact that the composition of velocity would give me that c is the same, even if there were already experimental facts. So Lorentz found them mathematically, but did not believe in them in the physics. He said it's just a mathematical feature that the Maxwell equations are invariant at a different set of transformations. It was Einstein that somehow, he knew the work of Lorentz, but it was Einstein that somehow realized that putting this postulate would immediately bring in a lot of new stuff that is this. So now, okay, now let's do composition of transverse velocity. So that means we have our particle whose velocity is w. Let's suppose it has a component along y. And we want to see how it relates to the new one. Now, let's do the inverse of this. It's one of the homework. Let's do the inverse of this. You get t equal t prime plus v c square x prime 1 minus v square c square. And then from here, I did the inverse of this. Do as homework is indicated in the pages as homework. You do the inverse of this. Now let's take the differential, and we get dt equal dt prime plus vc square dx prime minus 1 over vc square. You see, from this transformation, you should notice that now time is not an absolute parameter anymore. It involves x. So basically, people talk about space-time transformation, because here space and time are mixed one with the other. Okay. Okay, now let's insert this and this. That immediately implies dy prime is equal to dy here. So we have dy prime over dt prime plus vc square dx prime 1 plus v square c square. And you get dy, let's divide everything by dt prime, 1 plus vc square dx prime dt prime, 1 minus v square c square. Now, what is this? This is w prime y. Then I have divided by this. There is something wrong in a sign, but let me. There is a problem with the sign. Please do check my calculation. Okay, this is the transformation for transverse velocity. So transverse velocity change in this manner. Sorry, this is Vx. This is Vx. So you see, even transverse velocity change. Even if we are moving along x, the transverse velocity of my particle change is not invariant anymore because time change. So the manner it changes the following. Here it seems there was a plus, and I don't know why I lost it into a.
This one is minus. Yeah. Minus v over c square x prime.
This, you mean? Yes. Is plus. Plus dt prime is plus.
It's minus square root.
Oh, yes, of course. and here is plus. Here is plus. But it's not right. Okay, there should be a minus. Just work out, because this is the manner to do some gymnastic with these things. It's very important for the homework, okay, to learn how to do this gymnastics. So note, different than in the Galilean case, in the Lorentz-Einstein case, the transverse velocity are not left invariant even if we move along x. Why the velocity along y of a particle should change? It should not change because we are moving only along x. Instead it changes. Okay? Note this. Now let's go. So this is important because we will use later on. Tomorrow we will use this transformation. But now let's go to one more important. Sorry. You will find in the note, okay? In half an hour when we are finished, you will get it. Now, another consequence of this is what is called contraction of length. And this is a very important issue. That is the one that Lorentz had already found and did not believe in it, and also Fitzgerald, an American one, had already found it. A consequence of the Lorentz transformation is the contraction of length. So let's take a rod in the rest frame or laboratory frame. Rest frame or laboratory frame are the same. Let's suppose this is my rod, and let's suppose this is its length. So in the laboratory frame, this is x2 minus x1. And in the now let's take a moving frame with velocity v, and let's measure its length. It will be x2 t prime minus x2 prime t prime, x1 prime t prime, because in the moving frame I call the coordinate and time with a prime. Okay, let's see what we get. Okay, now you can do the inverse of these, express x as a function of x prime and t prime, and what you get is the following I wrote before: x is equal x prime plus vt prime over c square, t is equal t prime plus v c square x prime 1 minus v square c square. Okay, so let's see x2 t prime. Note, the new length of this rod, you will see that is less. L is x1 of t prime, x2 of t prime. I take the same time, because when I measure a distance, I take the extreme of the rod and I measure at the same time. So t is the same. This is very important. So let's see, using this law, for example, x2 from this is equal to x2 of t prime plus v of t prime 1 minus v square over c square. And x1 is x1 of t prime plus v t prime 1 minus v square c square square root. Now let's take the difference of these two. We have x2 minus x1 that we know was the distance at length. Let's do the difference between the two right hand side, and what we get is x2 prime t prime minus x1 prime t prime, because these two cancel, and then divided by this 1 minus v square over c square. But what is this? This is the length in the moving frame. So we get L0 is equal to L 1 minus v square over c squared. That means L is equal L0 times 1 minus v squared over c squared. This factor is less than 1, so it means the distance measured in the moving frame is less than the distance measured in the rest frame. Now, I will not spend time here, but this seems just mathematics, that there is length contraction, that the lengths are not something absolute with in the Galilean case it was, because in the Galilean case v is less than c, this is basically 1, and then the length don't contract. Now, to what is due this contraction? Well, it's due to the mathematics of that formula, but Einstein found which is the physics behind. I will skip that for the moment. Is the manner you would measure a distance if you are in motion. Okay, imagine this road, instead of being at rest, this road, let's suppose that this road is on a train that moves, and you are on the platform, and you want to measure that road that moves. The only manner is that these send you a signal, these send you a signal, and then you measure. Well, because the two signals are sent, and the fastest velocity they can send it is the velocity of light, then there is all a construction that you can find if you read that beautiful book of Einstein, The Meaning of Relativity, that there is no other manner to measure a distance in a rest frame, a distance that is moving, than some set of operation that leads you to this formula. So I got this only mathematically, and I prefer to get it that way. But in The Meaning of Relativity, Einstein, this contraction again was not due to Einstein, was due to Lorentz and Fitzgerald, who did not believe in it. I mean, come on, distances don't contract. Instead, Einstein did a Gedanken experiment, that means an experiment in his mind, saying, oh, we would measure a distance, a road on a train that moves, and we are on the platform, and the only operation you can do, because again of this postulate, is said that the distance you get is less than the original one in the rest frame. Now let's look at these things, because not only this tells us about contraction, but it tells us also something else. Imagine that c is the maximum velocity that you can reach. Because you see here, if you had a v bigger than c, you would get a negative number, so an imaginary length. So c is the maximum velocity that you can reach. The distance would get an imaginary thing. Now there is an extra, so length get contracted, and interval of time get dilated. And now we will derive that, dilation of time interval. So I often, it happens at least that one question that I often ask is why c is the maximum velocity? Otherwise, in the contraction of length, if you had a velocity v of the frame bigger than c, you would get imaginary length. Now, time dilation is another phenomenon. Now let's go back to this formula, the one that we had before. Let's take this one. We get delta t is equal delta t prime plus vc0 delta x prime 1 minus v squared over c squared. Now let's suppose two events. This is the distance in space of two events. This is the distance in time of two events. Let's suppose two events take place in the same position, but one after another. One at time t1, another at time t2, but at the same point. Then delta x is equal 0. So we get delta t is equal delta t prime 1 minus v square c square. So this is the interval of time in the moving frame, and this is the interval of time in the rest frame. And you see that the interval of time in the rest frame is bigger than in the other frame, okay? So this is the phenomenon of time dilation. And there is a mistake again. No, sorry, we have to take this one. We have to take this one, not this one. Okay, so we get this one. Okay, so the two events take place in the same position x, but at different instant of time, and this is delta t. Okay, now you see that the interval of time in the moving frame is bigger than in the rest frame by this factor. Okay, because this factor is less than 1, but is in the denominator, so it's dilated. So when you move, in a frame that move, lengths are contracted and the interval of time instead are dilated. Okay, now you can ask, okay, well, time get dilated, length get contracted, but there is any quantity that remain the same? Yes. These are called invariant quantity. Now, in the Galilean case, what was invariant? The interval of time, because t, in the Galilean case, t was equal to t prime, so delta t is equal to delta t prime, so it was an invariant thing, and also in the interval of space were invariant. So these were the Galilean thing, but it's not so anymore in the Lorentz case. So this is Galilean things. So if I ask you which are the invariants, the things that don't change in going from one frame to the other in the Galilean case, the length, the interval of time, okay? The position is not invariant. You know, the position, the Galilean things is this without the denominator. The position change in the Galilean things. But if you do the delta x and there is no denominator, okay, then this does not change. And if they are, remember that when we took time dilation, we took time dilation or space contraction, we did the delta x, but the delta t we put equal 0 because we measured the two extremes of the rod at the same time. Okay. Now let's see in the Lorentz case, Lorentz-Einstein. This was not in the original paper of Einstein, and it was not in the original paper of but it was in a later work, and the one that is responsible for this is Minkowski. Basically, what is invariant is the following quantity. Even if you go in a moving frame, this quantity remains the same, okay? So this is the quantity, a combination of space and time that does not change under a Lorentz transformation. Now we will prove it. So length contract, time interval get dilated, but there is this quantity that does not change. And also its square root does not change. Okay, so now we will prove that this quantity is the quantity x squared minus ct squared is equal to x prime squared ct prime squared. If you do this strange combination, then things don't change. So let's start and let's do that calculation. Let's take the right hand side, x prime square minus c square t prime square. Let's insert this. We get x minus vt square 1 minus v square c square minus c square t minus x v c square square 1 minus v square c square x square minus 2x vt plus v square t square c square t square minus 2px v c square plus x square v square c 4 1 minus v square c square. So let's do this calculation. We get x square minus c square t square minus x square v square c square plus v square t square c square over c square plus 2x vt minus 2x vt over 1 minus v square c square. This cancel with this, and what you get is x square minus c square t square 1 minus v square c square over 1 minus v square c square, and so you are left with x minus c t square. So this is the proof that in the two frames this quantity is the same. So it's not true that, as people say, there are no absolute quantity in Einstein relativity. No, there are absolute quantity, are these. These quantity are absolute quantity. Now, of course, this is the distance from the origin. X is the, we could say in general, this. So an interval in x minus c squared plus an interval in time is the same. It does not change if you go to new coordinate. Okay. Now, of course, as this is the same, also its square root is the same. Now, this quantity has a name, and it's called, it depends how you look at it. If you look at it in this manner, you see that this has the dimension of delta x, and is called proper length. So proper length is delta x squared minus c squared delta t squared. But if you write in the other manner, that means the opposite of this, c squared, you write this manner, delta t square minus delta x square over c square, then this is called proper time, because it has the dimension of time, and also this is Lorentz invariant. Now, okay. Now, let's see if it has, besides having this geometrical meaning of this strange combination, if it has also a physical meaning. You see, let's take proper time, that is the one that we will use most. You know, basically this is the time in the frame that moves with the particle. That means you have a particle moving with velocity v. This is the time in if you are just moving with the particle at the same speed v. How can we prove that? No, let's see. Now, before going into, so let's take now only the mathematical meaning of this, and let's draw these. Before doing that, we will do next time. Just one thing I wanted to do, and is the okay. Let's do this drawing. Okay, this is the line x equals ct, this is the line minus x equals ct. Now, you see, if we take, let's take three different points, O, A, C, and B. You know, this distance is called space-like distance. It is called space-like distance because you see delta x is bigger than c delta t squared. So OB, or this distance, is called space-like distance. This one, delta x is equal to ct, so is 0. This is called light distance. This one, delta x is less than c delta t, and this is called time-like distance. These 2 points, okay, can be reached by A can be reached by a signal starting from O, even if the signal moves at a speed less than c. This one can be reached only if the signal moves at a speed equals c. This one can never be reached. You have to move at a speed bigger than c. Okay? So these one, they say, are causally disconnected. Or they say these are out of the light cone. The light cone is this area. Okay? Light cone, because here is light that propagates, and light cone is the one inside, and every point inside can be reached by signal moving at less than the speed of light, while points that are outside cannot be reached can only be reached by signal moving faster than light, and you see from there. So these are called space-like points, and also they are causally disconnected because you need a speed higher than the speed of light. Well, let's stop here.